Hello, Honors Chem students. Mr. Keister here with you again today. This is the video for Tuesday, October 6th, 2020, which I believe is our scheduled 33rd day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons in the order that those lessons are presented will remain the same regardless. So let's take a look at our do nows, today's schedule. You are to pick up a new help sheet for our next Mastering Chemistry online homework assignment. We are picking up energy calculations number 2, which involves multi-step processes. We're going to do that today. And then you are also to pick up your exam 2 review. Yes, we have an exam coming again soon. I said save a spot for 51. That's our lab that we'll be doing tomorrow. Your homework for today was to complete the energy calculations assignment. Hang on to that. Please check your answers. They are posted on the backboard if you're here in school, or they are posted on the answer keys page in Canvas. Both of those will be posted by 7 a.m. this morning, so make sure you check that. Extra work this week outside of class. The Unit 1 and 2-1 review assignment is the first review for the fall final exam. You were to work on that on your own time. That was due today at the beginning of class. That should be on my desk now. If you're here, if you're not here, you need to submit that to me electronically during your class period today, during your scheduled class period today. Make sure you do. You don't want this one to be counted late. It's worth a lot of points. Again, there was no answer key for this one, so hopefully you've been carefully checking your work along the way. So today I'll finish up with the procedures for multi-step energy calculations for both thermal and phase energy. You'll have an assignment over this that is due tomorrow, and I will be collecting it for a grade. Your next online homework assignment is now on Unit 2-2 Energy. It is due this coming Friday by 7:30 a.m. This coming Friday at 7:30 a.m. And our next exam is coming sometime pretty soon. I will have that information posted for you tomorrow. All right, posted for you tomorrow. I have already posted the study list in Canvas, though, based on how soon that's coming. It'll be in the next few days. All right, but I went ahead and posted the study list in Canvas. Anytime you're ready to start studying for that thing, the list is there. Make sure you refer to it, okay? All right, well, I think we're ready to get started, so let me pull up the board here. All right, so here is where we left off. So we are going to look at the energy involved in the conversion from ice all the way to steam, all right, all the way to steam. So this is going to be a heating curve, all right? So let's just go ahead and get that thing ready. And remember, looks like this. And if we're going from ice to steam, we're starting from solid and we're going all the way to gas. So we're going to hit all 5 stages of our heating curve. All right, so here again, we've got the solid phase, solid to liquid, which is melting, liquid to gas, which is boiling or vaporizing, and then the gas phase. Again, when there's a temp change, we're involving a change in thermal energy. That would be those steps there. And our phase changes, of course, are our 2 horizontally sloped portions of the line. So we're looking at 1, 2, 3, 4, all 5 stages of our heating curve. Now remember that for water, our melting point for ice is 0 degrees, and our boiling point for liquid water is 100 degrees. So we're starting in the solid phase right here in section 1. We are going to raise the temperature of the ice till we reach its melting point. Then we're going to melt it. That would be stage 2. That's called, remember, the heat of fusion. All right. Then we're going to run it through the liquid phase. We get all the ice melted. We're going to run it through the liquid phase till we get to 100 degrees. Then we're going to boil it, and that is called the heat of vaporization. That phase change is called that. Okay. And then once we get it all boiled or vaporized, we're going to continue on into the gas phase. So I've listed here the various specific heat capacities. For ice, it's 2.06. For liquid water, 4.184. And for steam, 2.02. And I have listed our two phase change constants. Heat of fusion of ice, 334 joules per gram. Heat of vaporization of water, 2,260 joules per gram. So again, heat energy is added during this entire process. It is therefore endothermic, all right, which means Q is going to be positive, all right? Q is going to be positive in each and every one of those steps, all right? So let's go to the next page and do a couple problems. Oh, well, never mind. I guess we're going to look at the reverse first, all right? So for the reverse, we're now looking at a cooling curve, all right? We're looking at a cooling curve, and which looks just like so. All right, so temperature in Celsius and time. So now we are looking we're starting off at steam. So we're starting off in the gas phase. We're going gas to liquid, then the liquid phase, then liquid to solid, then the solid phase. So again, thermal energy, where all of our temp changes are, and phase energy, where our phase changes are. So again, now we're looking at 5 steps. We're going to go all the way from gas to solid. Now, our temps are the same here, 100 degrees. We're talking about water again, 0 degrees. But now, instead of the boiling point, this is the condensation point. Instead of the melting point, this is now the freezing point. All right. So now we basically are running the opposite way. So we're taking the gas, we're going to cool it down. It's going to condense at 100 degrees. That's its heat of condensation. All right. Then we're going to run it down the liquid stage here. Then we're going to solidify it or freeze it. All right. Heat of solidification, which would be there. Heat of condensation, which would be there. And then we're going to cool the ice down even farther. So now heat energy is released during this process. All of these are then for exothermic, which means Q is going to be negative. And realizing that Q is not actually negative, there is no such thing as negative energy. However, the negative sign indicates the direction in which energy is flowing, which is out of the system. It's being released, okay, or removed. All right, so we're going to use 2 heat energy equations involved here. Of course, if we have a thermal energy change, which is within a singular phase of matter, we're going to use the heat equation, Q equal mc delta T. And if we involve a phase change, then of course, now there is no change in temperature. And so we're just using the phase change equation, which is Q equals M times the heat of something. Could be heat of fusion, heat of vaporization, heat of condensation, heat of solidification. The subscript letter is different for all of those, but it's the same equation. All right, same equation. So we'll use that during any of our phase changes. All right. So the key to solving these problems is this: drawing the graph first, so we see how many stages out of those possible 5 stages are involved. Could be 1, could be 2, could be 3, could be 4, could be 5. That's where being able to draw the graph correctly is so important. Once we know how many stages are involved, then we have an equation that we can use for each of those stages, do our calculation for Q for each of those, and then add them up, and that gives us our total. All right. All right. Well, let's give it a whirl, shall we? First one says calculate the amount of heat energy required. So we're looking for Q to completely melt. That's a critical statement there. 3,400.00 grams. So there's our mass of aluminum. It's at an initial temperature of 20.0 degrees. So there's our TI. All right. So let's draw the graph. That's what we got to do here to figure out what we're doing. So here's temperature and here's time. We're starting out at 20.0 degrees. So we're going to heat this thing up and we're going to completely melt it. All right. So we're going to start here and heat it up, and then we're going to get to its melting point, which according to this piece of information right here is 660 degrees. All right. And then, but do we stop there? No, it says we're going to completely melt it. This point here is where it starts to melt, but now we got to run it through a phase change, which will completely melt it. All right. So we're going to end up right there. All right. So it looks like we have 2 stages to complete. This, of course, involves thermal energy. This involves phase energy. All right. In this case, the heat of fusion, since we're melting. All right. Well, according to our graph, we got 2 stages. That means we have 2 calculation steps to do. So step 1 involves our thermal energy change. That's Q equal MC delta T. And step 2 involves our phase change. That's Q equal M heat of fusion, or HF. So now we'll throw the numbers in there. 3,400.00. Specific heat of aluminum, 0.909. And our delta T, well, our initial temperature is 20.0. And as you can see right there, our final temp for step 1 is 660. Remember, it's TF minus TI. All right, so it's 660 minus 20.0, which of course is 640. So if we multiply those 3 numbers together, no rounding yet, 1,977,984 joules. An intermediate step, we're not rounding it. Okay. Second step, mass is the same, 3,400.00. And now our heat of fusion of aluminum is given 370.4. Multiply those, again, no rounding, 1,259,360. So we now know the amount of heat required for each of our 2 steps, which covers our 2 stages on the graph. Now we just simply need a total. So we add them up. And when you add them up, we get 3,237,344 joules. Now the question is, how do we round that? Well, this is the whole number. We're adding, so that's by precision. So this goes out to the whole number, the ones place. So does this. So we round to the ones place. That's where we're at now. No rounding required for this one. All right. So this is the whole number or the ones place. That's exactly where we're going to leave it. Okay. All right. That's the first one. Let's do the next one. Number 7. Iron melts or solidifies at 1535 Celsius. Calculate the heat energy released. Wonder what that means. I think that means that Q is going to be negative. We're going to come out that way. By a 10,000.00 gram sample of molten iron. That is liquid iron. So we're going to start in the liquid phase. It's at an initial temperature of 1,600 degrees. So that's TI. And we're going to cool it down to room temp 25.0, which is TF. Again, we need to draw our graph first. Let's do that. Temperature in Celsius and time. Okay, we're starting at initial temperature of 1,600. So that's up here somewhere. 1,600.0 degrees. We're going to cool it down. So now we're going to head down in the negative direction. But how far are we going to cool it down? Well, we're going to cool it down to where that iron is going to freeze, which according to this is 1535 degrees. So we're not going down a whole lot. 1535. And then we're going to freeze it. All right, so that's our second step. All right, but we're not done because we're going to take it all the way down to 25. So now we're adding a third stage. We're going to run her all the way down here to 25.0. So way down there. So it looks like we got 1, 2, 3 stages, thermal energy here, phase here, and thermal here. So again, we're going to cool the iron down to its freezing point. Then we're going to freeze it. And then we're going to cool it down further to room temperature. 3 stages means 3 steps in our calculation. All right. So step 1 is a thermal energy change. So that's Q equal MC delta T. Step 2 is a phase change, which is Q equals MH. This is freezing. This is called the heat of solidification. Step 3 is a thermal energy change. Again, Q equal MC delta T. So 3 stages, 3 steps, 3 calculations. All right. So now we'll plug the numbers in. The mass, 10,000.00. Specific heat of liquid iron. Be careful. There are 2 specific heat capacities listed here. We are in the liquid phase initially. All right. So we need to make sure we use the right one. Be careful of that. 1.697. And then T final minus T initial. Look at your graph. Our final temp in stage 1 is 1535. And our initial temp is 1600.0, which is negative 65. What'd we say? Looks like we're going to get Q as negative. Well, shouldn't we? Slope's negative. I mean, shouldn't the number match the slope? I would think it would. All right. Again, no rounding. Negative 1,103,050 joules. Next one. Heat of solidification, our phase change, mass 10,000.00, and our heat of solidification, negative 246.4. Negative 2,464,000 joules. Negative again, should be. Heat's being removed, all right? Got to take heat away from the iron to freeze it, all right? And finally, cooling it down more to room temp. Mass the same, 10,000.00. Now we need a specific heat capacity of solid iron. We're now in the solid phase. Again, make sure you get the right one, 0.448. Okay, now our final temp in stage 3 is 25.0. Our initial temp was back up here at its freezing point, 1535. So it looks at negative 1510 is delta T. And again, answer, negative 6,764,800. 3 negative answers, as they should be. All right. Our Q total, negative 10,331,850. Now, how do we round it? Well, here again, whole number, whole number, whole number. Every one of those, whole number to the ones place. Doesn't require any further rounding, all right? So that is our answer. However, remember that in reality, energy is not negative. It's just telling us, the negative sign is telling us the direction of the energy flow, which is being released or removed. And so this is equal to 10,331,850 joules released. Make sure you write that in. All right. Do not leave it as a negative answer. I want you to understand what that negative answer means. Okay. Doesn't mean that it's an answer less than 0. That's what I want to make sure you understand. The negative sign is simply telling us the direction of the heat flow, which is out. Okay. One more, and we are done with today's examples. All this erased here. There we go. Okay, sample of ice with a mass of 46.0 grams. So there's our mass. An initial temperature of minus 58.0 Celsius. There's our TI. How much heat energy required? Looking for Q again. To convert this sample to steam at 114. T final, 114. So we're going from ice to steam, all right? Well, what does that mean? We're going from the solid phase all the way to the gas phase, which means we're going to hit all 5 stages. So let's draw that in. So we're starting, let's see, T in Celsius and time. We're starting way down here at minus 58.0. So we're going to run it up to the melting point of ice, which is 0. Then we're going to melt it, and we're going to run it through the liquid phase, which will end when the water boils or vaporizes at 100. We're going to vaporize it, and then we're going to run it up some more, way up here to 114.0 degrees. So we're looking at all 5 stages, 1, 2, 3, 4, and 5. Thermal energy in each of the positive slope stages, phase energy in each of our phase changes. So 5 steps, or I should say 5 stages to the graph, 5 steps in the calculation. This is the maximum number of steps you would have, and that would be 5. All right, 5 is the maximum. Just a point here, I won't put a 5-stepper on the test because I know the amount of time it takes to do one, but you need to see how it's done because you probably got one on your homework, and I'm sure there's one in mastering. All right, I have that, I have no doubt. So steps 1 is Q equal MC delta T, that's thermal energy. Step 2, Q equal mass times the heat of fusion, that's melting. For our first phase change, step 3 is the liquid phase, Q equal MC delta T. Step 4 is the second phase change, which is boiling, Q equal MH of vaporization. And step 5, we're going to run it up higher in the gas phase, MC delta T. Our mass is the same for all of them, 46.0, so I think I can go ahead and put those in. All right, step 1. We're down in the solid phase. We need a specific heat capacity. Again, make sure you get the right one. All right. So it looks like we're in the solid phase, so that'd be ice, 2.06. And now what's our delta T? T final minus T initial. Well, look at your graph. The final temp for step 1 is 0. The initial is minus 58.0. So we have 0 minus negative 58.0, which of course is positive 58.0. Better be positive. Looks like the slope's positive. Answer there, 5496.08 joules. Again, no rounding there. Okay. Second step is our phase change. We're melting it. Again, we got two phase changes here, so make sure you get the right one. Get the right constant. This is for heat of fusion, which is 334 for ice. 15,364 joules. Step 3, back to thermal energy, Q equal MC delta T. Now we need this. Now we're in the liquid phase, so we need the correct specific heat capacity constant for liquid water, which is 4.184. Again, I can't say enough. Make sure you're using the right constants. If you're not sure which one, look at your graph. It should tell you which one it is. Where does step 3 end? Stage 3 end? 100. Where to begin? 0. So our delta T is 100 there. 19,246.4. Again, we're not doing any rounding yet. Not yet. Our step 4 is our vaporizing or boiling phase change. Correct constant there, 2,260. And that comes out to 103,960 joules. And our last step is we're in the gas phase, thermal energy. Gas specific heat capacity is 2.02. What's our delta T? Well, we're ending our T finals at 114.0, and our initial temp for this step starts at 100. So delta T is 14. 1,300.88 joules. So we got 5 numbers to add up there. Comes out to 145,367.36 joules. Now, how do we round? Well, we're adding, so we're rounding by precision. So we got the hundredths place, the ones place, the tenths place, the ones place, and the hundredths place. Which is the least precise? The ones place, or the whole number. So that would be 145,367 joules. That's by the whole number, or the ones place. Okay? So here are some calculations involving multi-step energy problems, all right? The key to this, I'll say again, is to draw the graph first. Draw the graph correctly so that you can see how many stages you're dealing with, all right? Pay attention to phase change temperatures, all right? That should then tell you the number of stages involved, which would then tell you how many steps you're going to need in your calculations, all right? And again, your positive and negative signs should match the slopes on your graph, all right? If heat's being added or absorbed, then everything should be positive. If heat's being removed or released, everything should be negative. If your numbers don't say that, you're doing something wrong, all right? So be careful. Be careful. So you got an assignment for this, which is due tomorrow. I am collecting it. You got a new mastering to get going on. You got a review to start. We got a test coming up here pretty soon. I will post that information in I'll post the information on when the test is tomorrow. But I've went ahead and already put the study list in Canvas so you can start knowing what it is you need to know for that test. So got a lot to do in the coming days. Got a lab tomorrow too. So let's stick with it, shall we? So until next time, this is Mr. Keister saying so long. Take care. Stay safe. Keep working hard and stay focused, my friends. And I will catch you next time. See ya.